Hi there, my name is Ian Rogers, and I'm the Chief Experience Officer at Ledger. Ledger Stax started shipping today, and we can only hope that you're as happy to receive your Ledger Stax as we are to send it to you, because it's been a long journey. We announced Ledger Stax in December of 2022 with the intention to start shipping it in March of 2023. But complications building this first of its kind curved e-ink touchscreen have delayed us a full year. But through the hard work of people at Ledger and at our suppliers around the world, we've done what many people, frankly, didn't think was possible. We've brought the world's first organic TFT curved, secure touchscreen to mass production. It's in Ledger Stax, and soon in your hands. We appreciate your patience, and we feel that you deserve an answer to the question, what took so long? Now that we're shipping, we can tell that story. This video is meant to bring you a comprehensive and definitive answer to that question. For this video, we spoke to Tony Fadell, the inventor of Ledger Stax, as well as the iPod and Nest, Pascal Gauthier, who's Ledger's CEO, Charles Guillemet, Ledger's CTO, as well as Johnson Lee, the CEO of e-ink, who makes e-paper products that you're so familiar with, and a whole cast of characters who can pull together the full story for us. You know, every great story has people, conflict, and ultimately resolution. This story has all three, and thankfully, a happy ending. I hope you enjoy it.
You potentially could change the display industry. These organic processes are like a dream in the display world.
In the case of choosing an organic TFT, we were about a year ahead. Why did it take longer than we thought it was going to?
Making it under 100 degrees, that's unheard of.
If 1 out of 1 million pixels is bad, the device is bad. We have been unlucky. I mean, the fire, the earthquake.
No one has ever really taken that to mass production.
None of us were certain if this product would come to market.
This was the hairiest thing I have been involved with in a long time.
Look, this device definitely wouldn't exist without Tony.
I'm proud to announce to you today, Ledger Stax.
Tony did choose a very challenging path on this by choosing a display that had never been done before.
Can we make a credit card-sized device that can hold all your digital assets on different versions of Stax?
I am Pascal Gauthier, and at Ledger, I am the CEO.
I led the seed round back in the end of 2014, beginning of 2015. Like I understood that the private key was the secret, was sort of everything, and losing the secret would lead to ultimately losing your Bitcoin.
Is Ledger Stax a milestone for Ledger and crypto user? I think yes. It's definitely a milestone for Ledger. We are making crypto always secure, but this time much easier to use.
I'm Charles Guillemet, I'm CTO at Ledger, and I joined the company in 2017. And my background is really cryptography and security. These are topics I'm interested in since I'm 12, so I spend my whole life on these questions. As a user, when you sign a transaction, you want to be able to verify what you are consenting. And this is really why we are using a secure touchscreen. And this touchscreen is directly connected to the secure element. This is the world's first secure touchscreen. This is really a secure circuit. It's made for security. And we spent several months in R&D trying to figure out if it was possible to drive a touchscreen directly from the secure element, and the answer is yes, it's possible. On the Nano S, X, S Plus, and so on, we had 2 buttons that are the secure inputs, and we wanted to replace those 2 buttons by a touch UI. And so this is what we did, and the touchscreen is directly connected to the secure element.
If Ledger alone had built this device, then it would not be this beautiful. If Tony alone had built this device, it would not be this secure.
How can we make sure that you can know it's yours without having to use battery all the time. And that's where I came up with the idea for Stax.
There were two things with this device when you brought it to us in terms of design. One was you said it's really got to communicate value, and that's why it should be the size of a credit card, the size and the shape of a credit card.
It was, how do you represent that this thing is valuable? And how do you say you're going to have more than one, right? And how are you going to make sure that it's convenient to use, right? So you wanted to make sure, that it was small enough, but it was still usable with a touchscreen keyboard and touch and all that stuff, and you could read it, right? It communicated value. It was pocketable, which was like credit card was speaking, right? And then you were going to stack them, and I was like, oh, wait a second. You stack value, and I instantly saw a stack of cash. And a stack of cash with bands around it, regardless of the type of currency, right? So it was like a stack of credit card sized devices that you could read on the side, because when you put them together, just like you do with a stack of cash, you can see the denomination of the bills and how much is in the stack. It's also relates to something in the real world that already exists.
I think in the case of choosing an organic TFT for Ledger Stax, we were about a year ahead. We announced this product in December of 2022. We thought we were going to be launching it in March of 23. And now here we are shipping it to customers in May and June of 2024.
And it's only because the team showed a lot of resilience and everyone showed a lot of patience that we are where we are.
My name is Johnson Lee. I'm from E-Ink Holdings. I'm currently the chairman and CEO at E-Ink Holdings. So we're the ones that make the display for the Amazon Kindle. Our technology is based out of electrophoretic displays. Some of you might wonder, what is electrophoretic displays? So basically, it's a bistable technology. It's like looking at a capsule or a ball where there's two pigments that's inside, or ink inside a enclosed capsules, where you use electricity to move these ink around. And basically, these ink remains where they are until you give them electricity to move them. The funny thing is that these are micro levels, so these are thinner than your hair. So a Kindle display uses a glass TFT that's based out of amorphous silicon. And for Ledger, it's truly amazing. It's actually the first company that ever took a plastic display out of an organic TFT process into mass production. So it's like Kindle, but it's under a flexible display that's made out of organic materials. And it's actually more environmental than the amorphous silicon displays you see out there. The TFT is on plastic, right? So it's less prone to cracks and breakage. Like for glass, if you smash it hard enough, you'll crack the glass. Because it's on plastic, you don't need a metal case behind the glass display to hold it, so it makes the whole thing a lot thicker. So you can do a really sexy design from a device perspective.
I had always wanted to do e-ink displays. So I know e-ink was possible, absolutely possible. But when I had the idea for Stax as, a set of things that would stack up and that you could look from the side to see what was on the side of the devices, we could put a screen on there, but it was like, okay, a screen there, a screen there. I was like, no. So I wanted e-ink, and I knew that e-ink could wrap, right? So I knew e-ink could wrap like a 30 degrees wrapping. But I'm like, wait a second. I know that there were teams, because I remember from my previous experiences, there were teams working on plastic displays. So we literally didn't make transistors on plastic, and then that could bend dramatically. And I knew that if you put a TFT display or TFT backplane with an e-ink, you could make it work. So I'm like, oh my God, let's see what we can do. So I had to go figure out what was the latest in plastic electronics, right? Being plastic on transparent plastic, and where e-ink was, and seeing if this was possible. But could they do the 180 degrees like we needed for the design? So that's where I started, because I knew the technologies existed. I didn't know if it was productized yet and manufacturable yet.
That sounds like almost impossible to me when I first heard about this. I thought that was quite innovative, but at the same time was quite challenging, because no one ever in the world ever produced an organic TFT. And then that's also curved in such a way that that's unimaginable. The whole concept of organic TFT, how it's going to be more environmental than other technology that's out there.
The E-ink backplane, the thing with the black and white dots, that was already on plastic. So that was already like, oh, that can be done. So after I went to E-ink and found out what the latest and greatest was. And so I was like, okay, where are we going with this? So I talked to various different companies, and they had done that 30-degree display, that 30-degree wrapping display with ink. But can we make it 180 degrees? And so that company went off and noodled a bunch, and we went back and forth about, well, how are you going to drive this screen? How is it going to be mounted on the mechanical chassis? How is it going to be assembled and make sure there's no bubbles in it? Is it going to be in a right cost dimension? Ultimately found somebody making displays, e-ink displays that were wrapping, and then that same company said, yeah, we can make it wrap all the way. And then I had to get comfortable that they could really do that.
Chuck Milligan, I'm an American in Cambridge at FlexEnable for the last 9 years. The technology spun out at Cambridge University in 2000.
2000, so almost 25 years ago?
Almost 25 years ago, that's right, which is not unheard of for, deep tech and new materials technologies. I mean, that's not dissimilar from the path that liquid crystal displays and then OLED displays went on. So what spun out of Cambridge University was a small team that was working on organic transistors. And this is a group that was led by Sir Richard Friend, who's, the godfather of organic electronics, and by Professor Henning Searinghouse, who is the world's greatest expert in organic transistor technology.
I have been hearing about plastic semiconductors since I saw them first in 1995, 96 at Philips Research Laboratories in Eindhoven, when I got a presentation of plastic electronics in 1995. No one had, over all of that time, except if they were really, really big and really slow electronics, made plastic transistors, transistors on plastic work for decades.
And so they spun out with this idea of making large area electronics. So, not the kind of integrated circuits that go into a computer chip, but the kind of electronics that can be spread over a large area to drive the display in your notebook or your phone. So it's fundamentally a different technology. It's about activating an area rather than getting as much functionality you can into a very, very small chip. And the dominant technology for doing that a while ago was amorphous silicon, which is a silicon-based transistor technology, but amorphous, so it could be spread over an area on a glass substrate. And that's the technology that's been driving most of the world's notebooks and TVs, for many years now. And the idea with the organic transistors was to, rather than using silicon, which is, brittle, and glass, which is, of course, heavy and thick and brittle, can we do this in plastic? Can we take advantage of the fact that there are polymers that can be built in a way so that they have semiconductor properties that can be super lightweight, unbreakable, super thin, super curvable? And so that's always been the vision of the company, is getting rid of glass in large area electronics. You can activate surfaces like ledger stacks, like wearables, like wrapping displays around pillars in airports or smartphones, just using traditional liquid crystal display technology, but enabling form factors that, glass and silicon transistors can't do. So it actually ends up being also the greenest display technology out there, because we're using a lot less energy to make the displays. And of course, we're not using and transporting glass like you do in glass-based displays. But it is a big change for fabs to go from running at 300, 400 degrees C to running at all less than 100 degrees C.
Making it under 100 degrees, that's unheard of. Like, for example, for our amorphous silicon, we do it at 350. And even with LTPS or LTPO, that's been used for OLED displays for mobile phones. They're built at 450 degrees C or 500 degrees C. And having a new process built into a fab, a TFT fab, it's not a small thing. It's actually pretty big. It's actually very difficult.
It's a 9 lithography step process, and there are probably 250 overall process steps, but there are 9 times that you're exposing to a mask and patterning. But 250 or so process steps. Any process step provides an opportunity for a particle to be a loose particle, to get somewhere into the stack. And because, you're driving this display with, vertical and horizontal lines that are only, tens of microns apart, a particle can end up creating a short or an open, which basically gives you a line out. And you've got some, 400 or 500 lines altogether, over a large area for this display. I know it's not a large display, but it is compared to particles of dust. And that has to be absolutely pristine throughout all of that processing, or you lose a device to yield. And so that's the tough thing about display. The tough thing about display is, one, defects are visible. So you can't hide. There's no error correction. There's nothing you might do in the IC world to end up with okay performance, because the whole function of this display is visual. So it has to be perfect or it's no good. And so if, 1 out of a million pixels is bad, the device is bad.
These organic processes are like a dream in the display world, but no one has ever really taken that to mass production. So when you want to be the first one in the world wanting to bring that to the world, I think you're going to have some challenges, because there's a lot of learning curve. What works in the lab is different from getting 1 or 2 pieces to work versus getting thousands or millions to work. It's a different story. It's a lot harder.
And this screen is one of the very first, if not the very first, complex transistor printed on plastic, not just display, but any kind of plastic electronics in the world. We made something that had never been done, and I had been watching it for 30 years. It's pretty crazy.
Our thought at the time was that between, and you were at Ledger Open with us, and we on the Ledger side really believed that there wasn't much risk in, between that taking an order and that ship. How surprised were you at how long it took? Why did it take longer than we thought it was going to?
These are advanced materials. These are fabs with, we're running hundreds of process steps. When you have a problem in manufacturing with advanced materials and doing something nobody else is doing, you honestly can't be sure. Is that a problem you're going to solve in 2 weeks, or is that a problem you're going to solve in 4 months? And some of them were longer problems to detect and solve. You have to change how all the equipment is run and maintained, and it's kind of getting to where we are is kind of like, the last mile in telecom. It's just that last mile can be awfully hard. We have been unlucky. I mean, the fire, the earthquake, we had some people in the supply chain go bust because, the display industry is tough. So we actually had to change suppliers midstream, which is not helpful in any way. So we did have a lot of headwind, and we got through it all.
If the partners hadn't believed in this, we wouldn't have been able to do it. Without the partners who are willing to invest in the front of that process and to actually, lose some of the output so that they could ultimately get to the good output, without them believing in the technology and the long-term viability of the technology and our product as being a path to this technology being used in, ultimately tens of thousands of different products, then this product wouldn't exist.
Though it's a very painful stage, it's 2 years ago or one year ago, but because of confidence about technology itself, because confidence about the product you designed itself, the first moment I see your product, it's really amazing me, actually. To be honest, it's a very amazing product. So I do think it's a bright future.
I think you're not just building a device, but I think because of the effort from Ledger, you potentially could change the display industry.
It's huge on many levels. It's huge on a motivational and emotional level. These also enable you to activate pixel by pixel, say, dimmers in the AR glasses of the future. So you've got something that's wearable that really dynamically can adjust what you're projecting to the ambient light, whether you're inside or outside. And I think that's uniquely enable the all-day wearability and performance that we need for the AR glasses to really take off. So there's a lot of stuff coming where we don't have to go through the same pain of years to get the transistor arrays working with good yield, because that's done. Now we get just to design new products around a proven manufacturing system and technology.
This was the hairiest thing I have been involved with in a long time. And I thought the multi-touch screen on the iPhone was tough.
Working with Tony on this was very enlightening. Like it's new, like you've never seen this before, and as the feel of touching the product is really great. So I really hope that our customers, when they hold their Stax in their hand for the first time, they'll be like, okay, I understand. Like these guys, they did something like very very different, and this is why the wait, and it was worth the wait.
The magic happens.
I think that the difference between resilient and stubborn is kind of in the results, right? If you keep doing the same thing and fail repeatedly and never find the end of the tunnel, then I think you're just stubborn. But if you keep improving, even if those improvements are small in the beginning, but in the end you go from sort of 2% output to 80% output, then I think you're just resilient.